right, so yeah, hi everyone. I'm very pleased to announce today's speaker, Michael Meyer. You could kind of argue that Michael started his career here in Heidelberg when he did his first postdoc in 1995 at the MPIA. And then he moved towards several stations going through Arizona and ETH Zurich. And yeah, now he's a professor and chair of the astronomy at the University of Michigan. And over the years, he built up lots of expertise in many fields, I think also including planets, stars, and life. So right, stage is yours, Michael.
Thank you, Jonas. It's very wonderful to be back in Heidelberg. It was my first postdoc here. And I'm here in part for a collaboration meeting, which is happening right now on the Königstuhl. So many of my colleagues with whom I work in this field of star and planet formation and exoplanets are not here. And so now I get to tell you what I really think, okay? So you get the secret version of this talk. Yeah, so I'm going to try to give an overview of the science that a group of us put together as part of an instrument team for the James Webb Space Telescope. I'll try to give you some kind of instrumentation motivation for why certain experiments are best done with this kind of facility and why it's not the best at everything. And so there are other kinds of observations that are better done with other facilities, which I'll describe. I'll talk a little bit about the history of James Webb, and I skipped some of the slides about the satellite itself. But if you're not very familiar with it, and at the end you want to hear a bit more, please ask. I have some backup slides I would be happy to show. Yeah, so let me go ahead and tell you my version of. So we want to use infrared observations, not just to get around extinction, but to look at intrinsically cool objects. The Planck function of cooler objects will peak farther into the red. And so we're able to see things that are cold, like planets and other cold bodies in the universe. Extinction is an important part of it. And this is an image of a planet forming embedded in a gas and dust-rich disk in the early few million years of a solar system or planetary system formation. And the main reason that was driving discussions of this new telescope in the early to mid 90s was the redshift, the cosmological redshift. As one goes back in time or looks back in time, the distance that the light has traveled and the stretching of the wavefront, if you will, makes you need to go into the infrared to see the main light from stars pushed into the infrared for very high redshift objects, which of course is a distance indicator due to the Hubble expansion. So for all of these reasons, it was clear that infrared was the way to go. And this led to the concept of the next generation space telescope. So this is a picture of the early science working group meeting in 1999, I think in Rochester, New York. And this is a much younger, lower mass version of me at the time. I was very fortunate as a postdoc, then a Hubble Fellow at the University of Arizona, to be involved in planning the first generations of instruments for JWST. And two main things that are kind of obvious when you think is, first of all, the background on the ground at wavelengths from 1 to 10 microns is orders of magnitude higher on the ground than in space. Everything in this room is glowing at a temperature of 300 Kelvin. This is peaking at 10 microns. And so it's a fierce background noise that I must fight against. Curiously, the instruments for JWST were only meant to go to 5 microns at first. And then with plots like this, just showing the extraordinary, 6 orders of magnitude gain, people were convinced to move to 10 and 20 plus microns. Of course, it's also true that the transmission of our atmosphere is limited in bands which are blocked by the molecules in our atmosphere that we would like to study in the atmospheres of planets around other stars. And so it was natural. We would love to go to space and look for water, carbon monoxide, carbon dioxide above the Earth's atmosphere, so we could see the bands that don't make it to us, even though we have some windows where we have some sensitivity. So already there was a formulation of what this should look like. Just to highlight, and this is for the students really, particularly observers who would like to quantify the gain in sensitivity and time. This again is the same plot I showed before of the ground-based background per unit area on the sky. And again, it's 6 orders of magnitude higher from the ground than in space. But if you look at a signal-to-noise calculation, where we are dominated by the noise from the background sky, we see that that's the denominator in this equation, where the signal is the signal rate of whatever object you're looking at. If you freeze the diameter of the telescope and look at a 6.5 meter telescope from a mountaintop at, say, 8,000 feet from the ground in Arizona, and compare it to James Webb in space, the only difference here then is the square root of this background rate. That means that JWST for a fixed integration time is 1,000 times more sensitive. And to make that up in time, it's the square root of the time. So it would take 1,000,000 times longer. So just fundamentally, you cannot do things from the ground that are doable in space. I'll come back to this calculation later when I talk about a ground-based 39 meter compared to a ground-based 6.5 meter, and a ground-based 39 meter compared to JWST. Okay, so I hope I've convinced you we need a James Webb Space Telescope, a 6.5 meter diameter aperture telescope in space, working from roughly 1 to 28 microns. And this was a combination of resources from NASA, the European Space Agency, and the Canadian Space Agency. And it was a wonderful example of the value of sharing intellectual information, of collaborating together, of being friends and not enemies internationally, especially for the pursuit of science. I love this picture because it really was a farewell. You know, it's the last picture that the spacecraft got of James Webb as it started its journey to the second Lagrange point, the unstable L2 point, where it needs to orbit around with some motions in a Lissajous figure. I started working on this in 1997, and we were involved in building the NIRCam instrument. I was a professor at the University of Arizona, and my colleague Marcia Ricci led an instrument proposal for NIRCam. And through this collaboration with Canada, these two instruments were very closely connected and coordinated. And so I was part of the instrument team for both of these. These were instruments that were confined to the 1 to 5 micron range in the near, what is referred to as the near infrared. And MIRI was a joint instrument build between the European Space Agency and NASA. So there was a joint science team between the US and Europe that worked very well together in the end. NIRSpec was built by the European Space Agency alone and is an extraordinary competent instrument providing spectra for many, many different kinds of science. So again, here's our wavelengths that we can see, and all of this is redder than that by a long shot. So when we won this proposal in 2003 and 2005, respectively, for NIRCam and NIRISS, we were invited to propose 900 hours of program time as the reward for spending 20 years building the instrument. And we split up into themes. There's a very deep wedding cake survey of galaxies going all the way back to redshifts of 15, trying to find the first light in the universe, really, called the JADES survey, which some of you may have heard something about. I was in charge of the star and planet formation group and involved in the exoplanet group. And our goal was to put together a kind of three-dimensional cube of science, where the three axes were age or evolutionary state of the kinds of objects we would look at, mass from tiny masses of individual objects to extraordinarily massive star clusters, and environment, trying to compare the star formation and planet formation properties in our own Milky Way galaxy, regions of clouds of gas and dust that form stars like our sun close to us, but also extreme environments where the metallicity is much, much higher or much, much lower, or that the stellar density is very, very extreme compared to what we can study within a kiloparsec. And it was meant to connect to people studying nearby galaxies and star formation in galaxies, but also to studying exoplanets from a wide variety of programs. You can assess for yourself how well we did in the end as I go. This is what probably is our last meeting. It was held just a couple of months ago in Arizona at the Biosphere Research Facility, which is a very fascinating place to visit. And we were led by my colleague, Marcia Ricci. Marcia is circled in red, and the reason she's not looking is because she's doing what she always does. She's making everything happen. So she's actually pressing go on a timed camera that was sitting on the steps and taking the photograph of all of us. But that was our team. We are much, much older and grayer than we were in the early days in 2003, that's for sure. It was a wonderful group to work with. And I have to say, you know, the night of launch, I was traveling with my family. It was Christmas time, and I was desperately trying to get a Wi-Fi connection so I could watch the launch. And it was partially at the end of the pandemic, so none of the hotel staff knew at 4 o'clock in the morning how to work the Wi-Fi, and so it was just a disaster. I was going crazy. But the 300 single point failures, you know, in the 30 days of terror during the launch, it was just extraordinary to see, after so many trials and tribulations, almost cancellation in 2013, to see it unfurl and work perfectly, almost perfectly. It was just extraordinary. No one thought everything would work as well as it did. So, wow, it was really a humbling experience to see what the engineers have provided for us. So as I go through the story that I want to tell today, I'm going to talk a bit about star formation from the pre-star forming conditions of the clouds of gas and dust in space. And I'm going to talk all the way through to planets. And for those of you who are not astronomers, I thought maybe some physicists would be here, perhaps not, but most of you who do study astrophysics will know the difference between a star and a brown dwarf at the hydrogen burning limit. No matter where the heat is coming from the formation of the object, there's a mass below which the central temperature will never get hot enough to sustain regulated hydrogen fusion into helium, and that we call a failed star or a brown dwarf. So that definition is easy and uncontroversial. The difference between a brown dwarf and a planet, however, in my opinion, is incredibly controversial. The International Astronomical Union famously held a democratic vote, of all things, on what we should have as the boundary. I was absolutely against this. I don't really care what people call one thing or another. I want to know how big it is and how it formed. And those are the things that we can hopefully learn through astrophysics. It's a formation-based definition, the difference between a planet and a brown dwarf, but that's what I have spent my whole life trying to figure out, and so that's the definition I will stick with. The overlap space between what could form like a failed star goes all the way down to something we'll refer to as the opacity limit for fragmentation. That means as an object is collapsing, it's generally cooling, and if it can remain isothermal, as the density increases, the fragments will get smaller and smaller. The so-called Jeans mass will drop as 1 over the square root of the density, but eventually the object can no longer cool because of the opacity. It's no longer able to cool, and that's the smallest fragment you can get. And Lyman Spitzer and many others calculated this 50, 70, 80 years ago. And for a solar metallicity cloud, that number is about 3 Jupiters. Could be 10 Jupiters, could be 7. Our magnetic field's important. There's a lot of astrophysics there. But you can form things all the way down to about 3 Jupiter masses. Conversely, planets could in principle form up to a fraction of the circumstellar gas and dust-rich disks from which they form. And that number is limited by gravitational instability. A disk can be maybe 10 or 20% the mass of a star. And so in principle, you could get up to 0.05 times the solar mass, or 10, 20, 30 Jupiter masses. So there's a huge overlap in the range of things I would call planets and the things I would call brown dwarfs. And that will be a theme throughout the talk. By the way, if you are curious about how to just estimate order of magnitude fundamental astrophysical bodies in the universe, just using the fundamental physical constants, there's a lovely paper by Adam Burrows and Jerry Oestreicher from 10 years ago that's worth a read for a student, maybe before your qualifying exam or something like that. Okay, so my definition of the difference between a planet and a brown dwarf is really formation, and it's really a story of bottom up or top down. Some of you will have already leaped to think of the top schema of pictures that I mean gravitational instability. And I do, but I mean other things too. Circumstellar or partially Keplerian supported disks that when I was a kid, we used to call pseudo disks, can also fragment and form things like that are binary stars or a star in a brown dwarf, and also turbulent fragmentation in a cloud. My good friend Ralph Klesson is not here. We were office mates up at the MPIA in the mid-90s, and he has done pioneering work on this idea of what is fragmentation. So there are many ways to form binary systems, and I believe that all of them, including gravitational instability, basically form a binary system where the lowest mass companion can be all the way down to the opacity limit. The bottom-up process is really the one that I call planet formation. And you start with dust grains like you might find, at least in my house, under the bed. And that grows up into a kind of critical core, which can then trigger the rapid onset of gas. Or if the gas is gone, you may only form rocky planets from a process of agglomeration. But it's definitely a bottom-up, not a top-down process. Okay, so with that astrophysical background out of the way, let me walk you through 5 or 6 of our programs, and hopefully you'll sense a flavor of how exciting it's been to get these data in the last couple of years. So we'll start at the beginning, where molecular clouds collapse under gravity, and that's balanced by their internal energy, and if they can dissipate that, the objects can collapse. Inside of those star-forming cores, one wonders what the transmutation of the elements is. We know in our sun what the abundance of carbon, nitrogen, and oxygen is, but surprisingly, in the interstellar medium, we are still a bit ignorant about whether carbonaceous grains are outnumbering silicate grains or vice versa. And even worse, we don't know exactly what the carrier of the dominant form of carbon in the interstellar medium is. And in fact, many people believe that the carbon grains that get delivered to the planet forming disks are made in these cloud cores. And so it's a very confusing story of the evolution of carbon in our universe into planets. Fun fact that not many people know, although one of the originators of explaining this to us was here, Hans Peter Gale, many years ago. Some of you may have known him. The Earth is underabundant in carbon by a factor of about 100 relative to silicon compared to the sun. So however this carbon is getting delivered into the nebula, it is getting lost in the process that forms planets. We think of ourselves as carbon-based life, and we are, but this is a carbon-poor planet. And that story of the carbon trail is, we don't know. We don't know the trail at all. We're just sniffing around. So one idea of how to start that story is to look at background stars through these molecular clouds with an instrument like JWST. We have a GRISM in NIRCam where we can take hundreds of spectra of background stars at the time, little pencil beams of light, and look at the absorption of the ices as a function of radius or ultraviolet penetration in the cloud, and try to find out what are the main carriers of carbon, nitrogen, and oxygen in the pre-stellar phase as a starting point to help us understand the evolution of carbon into Earth-like planets. And the wavelengths will shift depending on the matrices and local environment of, say, even water molecule in the ice form in these clouds. So this was led by my friend Klaus Hodap in Hawaii. And we started with pre-stellar cores, the funny red thing on the far right, again, looking through the cloud in the infrared. An object in the middle, which appears to be collapsing, but there's not yet a protostar there. And the final one, which I'm withholding from you, is a known collapsing protostar. So we know there's a hot energy compact object in the center. So we'll start with a look at that one. Well, boom, when we got these images, there's extraordinary energetic outflow activity in this protostar in the B335 cloud. And Klaus was able to, with historic data and HST, measure the velocities inferred by relative proper motions over decades timescale and find out that this protostar, as it's forming its first material, is ejecting about 10% of its mass on timescales of decades to centuries. So we are seeing outflows from that protostar that trace back to less than a century, given its velocity and how far away it is. And so Klaus was able to publish one of these very first images. You still see the streaks in it. We could do better, but you also can see some faint starlight shining off of the remnant cloud here. That we call that starshine. And that is another way to probe the material in these clouds, is by looking at the starlight reflecting off of it. Another example of a protostar. This is a work done on a different protostar with the integral field spectrograph of NIRSPEC. This white triangle is the field of view for the data that were collected here. And there are two protostars. There's maybe a disk or main angular momentum plane here, and there's an outflow around this object perpendicular to the rotational axis of the system. This I'm just showing you, it's another project that was led by Tom Green in our group. The top spectrum of this object, the northern object, shows that this ice spectroscopy works. It's a beautiful spectrum with water ice, carbon monoxide ice, and carbon dioxide ice, beginning to help us tell that story of what the abundances of these main carriers are. And eventually, I hope, we'll be able to trace that relative abundances of C, N, and O in these clouds. The bottom object is really in collapse. It's rapidly accreting, and we don't even see to the photosphere of the compact point source in the middle. We just see the accretion shock as the gas is flowing on top of it. Later, I'll show you carbon monoxide. This is the fundamental band of carbon monoxide, and you see this all in emission in this case. It's a beautiful inverted spectrum, and I'll show you the photospheric absorption spectra in a few minutes of different objects. Okay, so a lot of work still to be done on protostars. But if I move on to talk a little bit more about environment, I can show you some data from star clusters. And first, I'll just give a shout out to our colleagues who have been studying star clusters in our nearest neighbors, the Large Magellanic Cloud and the Small Magellanic Cloud, where indeed brown dwarfs have been identified pretty far down the mass function. And this was a subject of a nice press release by ESA recently. That's the Milky Way in the background in the upper right. And I just show that's what we are doing, is studying star clusters in the Milky Way. This is a region called NGC 1333. It's a star cluster of about 500 to 1,000 stars like the sun. It's relatively nearby at about 300 parsecs, and it's kind of intermediate stellar density. Sometimes we see stars forming in what we call T associations, which are very low density aggregates. And sometimes we see tens of thousands of stars forming within a few tenths of a parsec, like the Orion Nebula cluster, a much richer type of environment. This one is in the middle. And what we were trying to do with these observations is find these brown dwarfs all the way down towards this end, the opacity limit for fragmentation I mentioned before. And indeed, we found a few dozen of these. These observations were technically done in a special way, where we simply put a grism in the field of view and dispersed all the light together without slits. And for those of you who can think about why we use slits to block out background, these are less sensitive observations because of the overlapping background of all the spatial elements combined together. But there's a huge multiplex advantage by seeing everything in the field of view at once. So we saw a few dozen of these brown dwarfs, not a single one below 3 Jupiter masses, given the models to which we were comparing them. I'm not saying that's the absolute limit, but it looks like there is an end in terms of the luminosity. At a certain luminosity, below that luminosity, we just don't see any more objects. Whether it's 3, 5, or 7, I will not argue with you because our models are not that good. But we are starting to see an end of the IMF using that technique in this particular region. A slightly denser, slightly more distant, but somewhat similar star cluster is NGC 2024. If you're an amateur astronomer, you know the Flame Nebula, perhaps. It's beautiful, dark lane on the sky where it's very hard to see through, but in the infrared, things glow through a little bit better. This is the shorter wavelength mosaic to emphasize the dark lane and to show the beauty of the reflection and emission nebula that you see. So my student in Michigan, Matthew DeFurio, took on this project after his PhD thesis, in fact, and it was really the program that I wrote for the Next Generation Space Telescope in 1998. It's exactly the program I wrote, and here we are, almost 30 years later, doing the exact program. It still needed to be done. We can get down to about a half a Jupiter mass in this sensitivity of these observations. And Matthew did a great job of pushing this forward. I'll highlight a couple of fascinating objects here, which seem to have this ionized tail of emission, which are pointing towards sources of ionization into the cloud. Some people refer to these as proplids or protoplanetary disk sources. This one also is pointing to a different ionization source nearby, where its tail is going the other way. But the main story for me is this color magnitude diagram. So the magnitude of bright things at the top and faint things at the bottom is a measurement of luminosity. And this is a filter color, which is really a flux ratio, measuring the shape of the spectrum in the near infrared from 1.8 microns to 4.3 microns. And you see the dozens of objects we've detected. Again, not a single one below 3 Jupiter masses. But more importantly to that, Matthew did a very good job of doing a Bayesian analysis of these data, trying different models. A pure power law that just continues on to the end. A power law that goes up and comes down with a break in the middle, 2 slopes, and several other functional forms of this mass function. And by far, the evidence, we use multi-nest instead of MC for this, those of you who know these kinds of codes, the Bayesian evidence calculated far prefers the model that goes up to 10 Jupiter masses, turns over and comes down with an opposite sign slope. That is very strongly preferred from these data. It's early days, it's only a few dozen sources, and it's one observation, and it relies on our believing that our sensitivity down to a half of a Jupiter mass is what I say it is there. So we'll have to stay tuned. But we think this is the first published evidence of an actual numerical turnover near the opacity limit at the bottom of the IMF, which is something I had hoped we would do in the late 90s with JWST. All right, around each of those points of light in these clusters are circumstellar disks of gas and dust. They persist for a few million years, and that is the stopwatch you have to form gas giant planets. Once the gas is gone, you can't form a gas giant, although you may be able to form rocky planets, which are gas poor. These are not the best images of the high contrast imaging we've been able to do, but we've been looking very hard for small protoplanets or forming planets in these disks. This is one where it's clear to see these spiral arms in reflected light. And in this particular case, which does have those spiral arms, we have a candidate out here at a couple of hundred AU. It could be responsible for launching those spiral arms in the disk. We haven't been able to confirm it yet. Sometimes background objects can shine through, and so you need to be wary and cautious and careful and look over a couple of years for common proper motion to be between the companion and the source so that you know it's physically associated. So this is still a companion candidate at the moment. We had a program of 5 different systems that we pointed at in our GTO program, and most of them are published. Now there's a couple more still to come. I want to highlight the work of one of my former students from Zurich, Andrea Banzati, who's really become a leader in this molecular emission spectroscopy of circumstellar gas-rich disks. And one of the things that he started to find, even in his work some years ago, was that some of this icy material that's in the outer disk can migrate into the inner disk and evaporate or sublimate, such that the water vapor reservoir in the inner warm disk is very, very high. And if that were true, that would lead to the formation of something that we call water worlds, things with many kilometer oceans, with no surface land, which some of us think would make it very difficult for life to be formed on those planets. So we're also probing the composition of these gas disks, and we hope to confirm or refute these models of icy materials coming in and making the inner warm nebula extremely wet. I'll come back to this in another observation in a minute to provide a bit more context for the nature of the planets that would form in such a disk. Well, easy targets for us were objects where you have a 5 to 10 Jupiter mass companion out at, say, 100 or 200 times the mean Earth-Sun distance, an astronomical unit. These are unusual to have such a planetary mass body so far away from the star. And we wonder, are these really planets or are they brown dwarf companions? I believe the vast majority of them are brown dwarf companions, but it is possible that you could form a bottom-up gas giant planet in the inner system and have a multiple planet scattering event that would move one of these to much larger orbital radii. That would require having a slightly more massive body that stayed close in, and those are hard for us to see in these young systems. This is an example of an object B that's about 10 Jupiter masses. It's 200 times the Earth-Sun distance. It's about 100 million years old. And of course, the solar system is about 4.5. These objects, when you look at them young, they're still hot because they haven't dissipated their heat yet. And it's fun to look at cooling models for this, which you can do as a first-year physics student practically. Just assume that all of the thermal energy, is given by this formula here based on the mass, really, and calculate the number of atoms in this object of hydrogen, and then ask yourself what the cooling time is if it just radiates like a black body. And this is the formula that you would use to derive that. And something that would be 1800 Kelvin at 5 million years cools down to about 300 Kelvin at 1 gigayear. And if we saw such a thing, we would call it a Y dwarf. These are objects we've seen in the universe with far infrared missions that are good at detecting them, like the WISE mission. And if you let it cool even further, like our own Jupiter, at 5 billion years, this formula gives you 175 Kelvin. Okay, that's a little warm. Jupiter is more like 130, but such a simple formula works rather well. And it reminds us that when we look at these objects young, they're very hot, and that means they're super bright and much easier to see at the young ages rather than the old ages. So what are these things? Are they planets or are they brown dwarfs? Well, one way to test is to take spectra and assess their composition. Jupiter, for example, in our own solar system, is overabundant in carbon, nitrogen, and oxygen by a factor of 3 compared to the sun. It's a very extreme enrichment of those heavy elements, and we see it in the spectrum. So if we took spectra of these companions and they matched the composition of the primary or the star, we'd say, well, they're the same. They probably formed like a binary. Even though the companion is only 10 Jupiter masses, it's essentially a star with a very, very low mass brown dwarf companion. If, on the other hand, these spectra reveal extremely unusual abundances, we expect a lot of pollution in a disk which has the solids which end up in some of the planets, like in Jupiter. So that's our evidence for a bottom-up process. All of these squiggly lines are extremely high signal to noise. They have signal to noise of 1 to 300. All of these are real, and it's been overwhelming to try to deal with these spectra and find out what they all are. The top one is the object I just showed you before, this 10 Jupiter mass companion at 200 AU. And one of the funnest things a stellar astronomer can do, you look at two stars, in this case, planetary mass objects on completely different parts of the universe. And the spectra are so similar. You know there's underlying order and physics and chemistry to these things. This lower red one is an extremely similar planetary mass companion out at large orbital radii. And it gives a nice match, VHS 1256, capital A, capital B, little b. The nomenclature is bad. This middle blue spectrum, however, looks different to your eye. And that's a 5 Jupiter mass object at about 10 or 15 million years. But we believe it is surrounded by a not stellar disk, because it's really around a 5 Jupiter mass object. So I would like to call it a circumsubstellar disk, because the object with the disk is 5 Jupiter masses, and it shows this extremely long red behavior. Exactly the structure of a disk around such a small object. You might think of something like Jupiter and the formation of the Galilean moons. That's an interesting thing to think about. However, I personally believe that one is a brown dwarf as well. Its primary is 30 Jupiter masses, and the companion 5 Jupiter masses, so the mass ratio is only 6, whereas the mass ratio of the Sun and our Jupiter is 1,000. And I think that's the key difference between a binary and a bottom-up planet-like object, is that mass ratio. But if we push this, again, to look at this carbon monoxide, the CO fundamental, this is in absorption this time because of Kirchhoff's laws and the way the radiation is propagating through cooler layers above, and there's absorption. This is the fundamental. The first overtone is at 2.3 microns. You see several of the band heads, and there's even a second overtone in the middle of the H band, which you really can't see. But it's beautiful to see this molecular astrophysics play out for you in the spectra of these objects. Well, same masses, but let's look at a very different evolutionary state. I told you before at the very beginning that JWST is really, really good in the background limit. It's really beating anything on the ground in time to complete by a factor of 1 million. So it was always and I argued this at every meeting I went to, the best thing to do with JWST is look at faint primaries so that you're in the background limit at as small an inner working angle as possible so that you're always in background limited case. If you're fighting the light of a very, very bright star, you might be better off doing that from the ground. But in this case, we took the 22Y dwarfs. These are objects colder than about 500 Kelvin, found by the WISE satellite within a few parsecs, because they're very, very faint. And they're billions of years old, and we're looking for companions. We want to know the multiplicity fraction of such tiny cold objects. And this one, WO336, was the first binary we found. It's just at the pixel resolution, but of course, with high signal to noise, you can defy the diffraction limit, if you will. It's really not an absolute limit. It's really just a matter of you need high signal to noise to see residuals when you subtract a primary, that there's a real secondary there. If you assume it's a single, you get the top subtraction. The residuals are horrible. It's a bad model. If you assume it's a binary with a certain separation and flux ratio, we can make the thing go away. And it's a very, very nice fit to the data. And if we use the binary model and only subtract the primary, then the secondary is very clear and where it is. This is separated by about 1 pixel on the detector. And it's a 10 Jupiter mass primary with a 5 Jupiter mass companion. And they're both about 300 Kelvin because of their age. And they're separated by 1 AU. I just find it very fascinating that such a binary could be formed in the clouds of gas and dust between the stars. So this is challenging our understanding of star formation or brown dwarf formation and the story of the specific angular momentum of these star-forming clouds and how they lead to multiplicity. So we're publishing the statistics of this survey coming out next month, being led by a student in Montreal. But there's more to come. We've really just scratched the surface. And one of the things that JWST will be able to do that almost nothing else can do is to look for very tiny planets at very large orbital separations. And the reason, again, I say that is we've got to be in the background limit, because if we're fighting the bright light of a bright star, it's tricky to look for planets. It's hard to find a faint firefly around a very bright searchlight. But if you look at large enough orbital separations in the background limit, around stars that are tens of parsecs away, within 100 million years or relatively young, these background limited observations from JWST can get down to about 10 Earth masses. Basically, we could detect ice giants like Uranus and Neptune at 30 astronomical units, no problem. And there's really no other way we could find them. Radial velocity cannot do it. Of course, the transit probability is almost non-existent. Astrometry would be great, but Gaia will not really go out to stars or planets this low mass at greater distances to the sun than about 10 or 15 parsecs. So we really need these observations of stars at about 50 parsecs. And we were awarded 2 relatively large programs to cover about 200 stars with James Webb, looking for ice giants at large orbital separations. And those data are coming in now, and it's going to be very exciting to measure, even if it's an upper limit, to the ice giant frequency beyond 10 AU, which is what this program is designed to do. There's a nice paper by L. Bogat, a member of our GTO team, on a subsample of the 9 best M dwarfs for this kind of work. And indeed, she has proved that we could get down to about 10 Earth masses. with those data. So stay tuned, because that, I think, will be the only other thing that can get down there is microlensing. And there we're stuck to 1 to 10 AU. But in principle, we have a decent statistic of 10 to 100 Earth masses frequency in that zone. And very nice to compare that to these kinds of observations. Well, I think that architectures of these planetary systems are important and crucial, maybe, to the story of whether there could or couldn't be life in those systems. I mentioned before of all this water migrating into the inner system and creating this hot bath of water in which a planet might form. And there are observations. This is now a transit observation. So we're watching the planet move in front of the star. We're taking a spectrum through the atmosphere of the planet and trying to infer its composition. So we're watching absorption of light as a function of wavelength and seeing huge signals of water bands in this planet's atmosphere. And the inferred column densities mean that this object essentially has to be a water world with many kilometers of an Earth ocean and no surface. Some of us think that the twin miracles of life, which require metabolism and gathering genetic material so that you can reproduce yourself, require some kind of discontinuity, maybe a surface between a watery place and land, like Darwin's famous warm pond, where you can have concentrations that are super equilibrium, and maybe in lucky circumstances get to these things. But it's hard to imagine how you collect genetic material or start a metabolism when you're just in a bath of water completely. This observation was led by this graduate student, Caroline, in Montreal, but also with strong participation in Michigan. Ryan McDonald was a Sagan Fellow in my group. He has just taken a lectureship at St. Andrews. So he's in the process of moving back right now. And Ryan enabled one of our undergraduate students to participate in this discovery of this water steam world, one of the first identified by JWST. So that made his graduation year for sure, to be able to be involved in this discovery. Well, JWST is doing a lot. And we're just scratching the surface of what it really can do going forward. But it's not the whole story. There are other facilities that we need to unlock the secrets of star and planet formation and maybe even life. And one that is a perfect complement is the extremely large telescope, or the ELT, the 39-meter ELT under construction by the European Southern Observatory. Very forward-thinking decades ago to plan the way for this, to convince member states and council to go along with this investment. And it's a structure that will last for decades into the future and really revolutionize ground-based astronomy in ways maybe none of us foresaw decades ago. This is a picture from Wikipedia of a lot of big telescopes. Some of our favorites are there, the VLT at Paranal. This is James Webb, shown here. I mean, it's not terrible. It's a wonderful, amazing facility, but that's its aperture size. And of course, this is the ELT in Sierra Amazonas for scale. Extraordinary. But they have different roles. The James Webb Space Telescope is still more sensitive in the background limit than a 39-meter by a factor of about 30. It's an interesting interplay between background and aperture size. But that means the time to complete an observation, JWST still wins by the square of that number. It's a factor of 1,000. So JWST is still the most sensitive. It is great to have diffraction limited coverage over a large, relatively large field of view, just perfect, stable optics in space. And of course, the wavelength coverage can see things that are blocked by the molecules in the atmosphere that we want to see in other planets. And JWST can do that for us up above. The ELT has resolution, big, wonderful, high resolution in both spectral domain and spatial domain. And those twin attributes give it an incredible advantage for certain studies and others not so much. It will also be better at seeing faint things near bright things. And in fact, because the planet orbital distribution seems to rise as you go out from the surface of the star, peak at about 4 astronomical units and then go down again, our 8-meter telescopes that did hundreds of night surveys only found a handful of new planets because they are so close in. And the ELT will zoom itself into that peak and be able to detect the bulk of the planets and meet up with the radial velocity machines which are doing the same from the other side. So it's a beautiful synergy there for the spatial resolution of the ELT. Now, I am American, and so I have to show you a football stadium. This is what we call the Big House. It's the largest American football stadium in the United States. And this is how we sell this to our administration, the 39-meter ELT compared to our football stadium. About 8 years ago, we made a special arrangement with ESO so that we could contribute money to the instrumentation program and therefore become part of 4 instrument teams and have access to the guaranteed time that they will be rewarded with for building these instruments. I even had the good fortune of being able to do detector work in my lab in Michigan for the mid-infrared instrument METIS, which is the one that I'm here to work with on the Königstuhl this week. And I'm very proud to say that the University of Michigan is the only US institution with this kind of access to the ELT. We're very, very proud of that, and we hope that it will make us one of the top astronomy departments in the US going forward. We're in 4 collaborations. METIS I mentioned, which we're here meeting in Heidelberg this week. Harmony, which is an integral field spectrograph from 1 to 2.5 microns. Andes, an extremely high spectral resolution, near infrared and visible spectrograph at a resolving power of 150,000. And Mosaic, which is a relatively wide field multi-object spectrograph to take hundreds of spectra at once for studies of galaxy evolution. So this is really the future, we think. And the relationship between Hubble and the 8 to 10 meter class telescopes from 25 years ago, we are now going to reproduce that with JWST and the ELT going forward. So it's a beautiful synergy, and we're very fortunate to live in a time when we'll get to combine these 2 fantastic resources. So please stay tuned. There is just so much more to come. The mission seems like it will last for a while, more than a decade. We're into cycle 4, and we look forward to the next call for proposals in the fall for cycle 5. And thank you very much for your attention.
Briefly mentioned that there is some sort of underabundance of carbon in on Earth compared to the sun. Is there some sort of explanation for this?
Well, I first learned about it about 20 years ago. And at the time, Professor Hans-Peter Gale would tell us that carbon in certain forms, depending on the carrier, what structures it was in, could combust or burn at a temperature of about 800 Kelvin. And so if dust grains could come into the gas nebula close enough to the star, say a few tenths of an AU, there's a natural process by which the carbon would be liberated as it's attacked by OH radicals. I'm not a chemist, and I don't fully understand the details. But if that were to happen, the nebula is a very oxygen-rich environment, and so free carbon would naturally combine with oxygen and form carbon monoxide. And for decades, we have looked for a signature of a bump in the column density of carbon monoxide due to this liberation of carbon. We have not found it. My colleague in Michigan, Ted Bergen, believes that the form of this carbon is such that it will sublimate much farther out at a few hundred Kelvin. And Professor Thomas Henning thinks he's completely wrong. So I don't know what the answer is, but somehow there is a way that the carbon that is delivered from the interstellar medium to the disk does not end up in the solids that forms the planets. And we're still working on it. And JWST is helping tremendously as we see carbon-rich gas disks and carbon poor. So hopefully we'll be able to figure out the story.
Yeah, thanks for this wonderful talk. You were mentioning the brown dwarf binary YSO366, and you said, yeah, you were kind of highlighting its very specific role being so close and kind of old. I was wondering if this
orbital, well, we only have 1 point so far. But are we expecting that these binary orbits it might have right now is stable, or it changed over time, like some sort of co-evolution of those objects?
Well, it's a great question. So they're not sort of interacting, so they're not mass exchange, but there's already a story to be told in stellar binaries where the peak of the orbital distribution for A stars seems to be at hundreds of AU if you only go down to the hydrogen burning limit. So that is interesting because the sun-like stellar companions only down to the hydrogen burning limit peak at about 50 AU. And for M dwarfs, it seems to peak at about 20 AU. And although that's the only Y dwarf binary we have, you can look at late T dwarfs, and there's a sample from HST. It seems like the orbital distribution of Y dwarf binaries are peaked at about 3 to 5 AU. So there's kind of a story. Now, that may not surprise you if you thought that this was all orbital dynamics in star clusters because of the binding energy. And so maybe it's natural that wide, low mass companions wouldn't survive. That's part of the answer, but it's not the whole answer, because it's also true that the stellar densities of some star clusters that we study are not high enough to completely sculpt the binary population, as my colleague Pavel Krupa has argued for many, many years. So we are trying to tell this or test the same stories with brown dwarf companions. And the answer isn't written yet, but I think that the brown dwarfs are a very interesting example, not just because they're so tight, but it also appears that the mass distribution of companions is peaked more at 1-to-1, whereas for FGK stars, M dwarfs, and A stars, it's a rather flat distribution between about 1 and 100 AU. Outside of 100 AU, it looks like it's drawn from the IMF, which kind of makes sense if it's turbulent fragmentation, as Rolf studies. Inside of 1 AU, we think we see evidence of the objects must have migrated through a disk that surrounded the primary, and preferentially you will take mass onto the companion and drive the mass ratio close to 1-to-1. So stellar twins or M dwarf twins tend to be very close in orbital separation. And maybe the Y dwarfs are the ones that's all that's left. So I don't know yet, but there's a beautiful multidimensional problem with clear answers, because it's all just counting stars and brown dwarfs and planets and statistics. So I hope we're going to get there soon.
Thanks, Michael, for this great talk. And we appreciate your praise for the ELT very much. Of course, on your slide with the mirror sizes, the ELT had a label planned for 2020.
So let me go before the election and just tell you the normal part of the story, which is that for decades, the US has had 2 projects with very strong, powerful, important, wealthy institutions and great international partners and beautiful, wonderful telescope designs, and wonderfully in different hemispheres. So this was a great story to tell. And so many of us worked hard to sell the federal government on the story of the US ELT program, which would require both. And our way of competing with Europe and its 39-meter would be to have access to both hemispheres. This just fell dead. They didn't buy it, and neither project has even over half of the money. And any time the National Science Foundation has been asked to fill in the other half, they just say, no, we don't have the money. So both are kind of, I mean, the GMT will go forward at least with 4 unphased mirrors. And at some point in the future, we'll have first light, but I believe it will stay like that for maybe a decade. The TMT, we still don't know if we can stay at Mauna Kea, probably not, but maybe. So both are just really into the indefinite future. And so it really is the only game in town is the ELT for, I would say, decades. That's the good part of the story before the recent budget cuts. And of course, policymakers have every right to make those decisions, right? We're using public money, and there's important reasons to use it for different things.
Hi, thanks for the really interesting talk. I'm interested specifically in when gas clouds collapse into stars, right? What are like the timescales we're looking at from like the initial collapse to the fragmentation to
Well, the standard story is that the early collapse, we would say, happens on a free fall time. So a few times sound speed and 100,000 years, maybe 300,000 years. And then there's got to be a dance between the way material is gathered onto the star through the disk and the infall rate, which continues to build up the disk. So in my mind, this is a story of gravitational instability every so often. And at first you have a tiny protostellar seed, say 1/10 of a solar mass. You have a little disk around it. It fills up rapidly, very fast, and becomes unstable and dumps material onto the star and redistributes mass and angular momentum. Then the object in the middle is bigger. The disk fills up again, dumps, bigger, disk fills up again. And if you just do a numeric 21 times, you get to a 0.9 solar mass protostar and a 0.1 solar mass disk. And that's what I would call the last stable disk. Planets may or may not have formed in that disk earlier, but it doesn't matter because they all get whooshed into the star. And it's that last stable disk that is really the planet forming one. That time scale for that last disk is millions of years, but the early phase is quick. I would say the unwritten part, if there's, while you're moving, is I don't think we fully appreciate how the cloud cores gain their specific angular momentum and whether that is due to kind of random processes in a swirling dynamic cloud or whether there's something more ordered. The binary properties of higher mass stars tend to be a little different than the binary properties of lower mass stars, such that the specific angular momentum of more massive cloud cores should be larger. And my understanding, and Ralph, it's too bad he's not here, the main source of gaining angular momentum that I have seen in numerical simulations is somewhat chaotic. It's really just mixing cores moving around together in a sea of diffuse media. And it's really hard to get order of that in terms of the multiplicity properties.
Any other questions? No? I don't see any questions online. Okay. If not, then there'll be drinks with the students after the talk. So if you're interested to join, then just come on down here to the front. And I think there'll also be dinner a little bit later on. Is that right? So then just come on down and talk. Great. So then let's thank Michael again.